Welcome to Understand the Math. In this video, I'll walk through exam questions on linear systems of equations. I'll summarize the steps needed to solve each question and carefully work through every detail so you feel confident tackling these problems on your own. Be sure to check out the video description below for a free PDF download of all the questions. Let's get started. In the first question, we're given three augmented matrices that correspond to a linear system of equations. We're asked to determine if the linear system has no solutions, exactly one solution, or infinitely many solutions. If a solution exists, we're then asked to find the solution. The best way to begin these problems is by circling the pivots. So let's start with matrix A, and I'm going to go ahead and I'm going to circle the pivots. We have two pivots, and notice that this is an augmented matrix, so the next thing that we're going to do is we're going to draw a line so that we can see the left-hand side of the equations and the right-hand sides. We have two pivots, and then notice that our third row is a row without a pivot, and the right-hand side is equal to 12. This tells us that this equation here is 0 is equal to 12, and that can't be. So matrix A is one where we're going to have no solution. Let's now look at matrix B. Again, we're going to circle our pivots, and then we'll draw a line to separate the left-hand side from the right-hand side. In this matrix, we have three pivots. So this tells us that x1 is equal to 8, x2 is equal to 9, and then our x3 is equal to 2. We could have easily written this as x, y, and z. This matrix is an example of one where we have one solution. Let's look at the next one. We'll circle our pivots, and then we'll draw our line. In this one, we have two pivots. Our last row is just a row of zeros. So this means in the third column, we're going to have a free variable. And this means that we're going to have infinitely many solutions. Let's go ahead and solve for x1. We have x1 plus 3x3 is equal to 5. So that tells us that x1 is 5 minus 3x3. And then in our second row, we have x2 plus 4x3 is equal to 2. So this tells us that x2 is 2 minus 4x3. And we also know that x3 is our free variable because it corresponds to our column without a pivot. Because x3 can range between minus infinity and infinity, we're going to have infinitely many solutions for our matrix in part C. So let's just write down infinitely many solutions. In our second question, we're given four matrices, and we're asked to determine if they are in echelon form or in reduced echelon form or neither. Down below, I've written down the steps that we can follow. The first thing that we're going to do is we're going to circle the pivots, and then we're going to check if our matrix is in echelon form. If it's in echelon form, we have three requirements. The pivots are down and to the right. We have zeros below the pivots. And then if we have a row of zeros, it's going to be at the bottom. If a matrix is in reduced echelon form, these first three requirements in echelon form are met. And then we have two additional requirements. And those are that our pivots have to be equal to 1 and that we have to have zeros above our pivots. Let's go ahead and let's look at our first example. We're going to begin by circling our pivots. Our pivots are the first entry as you go from the left that's not equal to 0. So that's going to be 1 and 5. Notice that we have a row of zeros, but it's at the bottom. And then we have zeros below each pivot. Each pivot, however, is not equal to 1. Notice that this pivot is equal to 5, so this matrix is just in echelon form. Let's now look at our second matrix. Just like we did for the first one, we're going to circle our pivots. The pivot is the first entry as you go from the left that's not equal to 0. So those are our pivots. Right away, you might notice that this pivot is directly below the previous pivot, so the pivots are not down and to the right. So because of this, this matrix is not in echelon form and it's not in reduced echelon form. So we're going to write down neither. Let's now look at our matrix C. We'll circle our pivots. We have a pivot here, here, and here. Now let's look at the zeros below the pivots. We have a 0 here, here, and then notice that we also have zeros above our pivots, and our pivots are all equal to 1. So that's going to tell us that this matrix is in echelon form and it's in reduced echelon form. Whenever a matrix is in reduced echelon form, it's also in echelon form. Now let's look at part D. Just like we did before, we're going to circle our pivots. Our pivots are down and to the right. Let's look and see if we have zeros below our pivots. We have 0 here and here, so we do. We have zeros below our pivots. Now let's check for zeros above our pivots. We have a 0 above our pivot. Now we have to check and see if our pivots are equal to 1 in order to be in reduced echelon form. Notice that this pivot is not equal to 1, so this matrix is not in reduced echelon form, but it is in echelon form. In this problem, we're going to use matrices to find H and K such that the following linear system of equations has no solution, a unique solution, or infinitely many solutions. Notice that H and K are located right down here. To solve this problem, we're going to take our linear system and we're going to put it in echelon form. The reason that we're going to do that is echelon form is the form that we use whenever we want to find out what type of solution we're going to have. And then we're going to see what the pivots and right-hand side equal. We always want to begin this type of problem by taking our linear system of equations and putting it in an augmented matrix. Let's go ahead and do that. We have 1, 4, 2H, and then on our right-hand side, we have 3 and K. We want to put this in echelon form, so I'm going to circle our pivot, and we're going to have to get this 4 to be a 0. So the row operation that we're going to use is we're going to take row 2, and we're going to replace it with row 2 minus 4 times row 1. This is going to give us the matrix 1, 2, 3. The top row stays the same, and then we're going to pick up a 0. We're going to pick up an H minus 4 times 2, which is an 8, and then a K minus 4 times 3, which is a minus 12. And this is the matrix that we're going to have to analyze. Let's first look at when we have no solution. Whenever we have no solution, we're going to have a row of zeros equal to a non-zero number. So what we're going to do is we're going to force our left-hand side, h minus 8, to be equal to 0. And then we're going to force our right-hand side, k minus 12, to not equal to 0. So this gives us h is equal to 8 and k is not equal to 12. I'm going to go ahead and highlight this because that's our solution when we have no solution. Now let's look at what's going to happen when we have a unique solution. When we have a unique solution, every column in our matrix is going to have a pivot. So let's go back up and let's look at our matrix. And I'm going to go ahead and I'm going to circle our columns. Or in other words, I'm going to circle the pivots in our columns. We have to have every column have a pivot, so that means that h minus 8 cannot be equal to 0, and that will make sure that we have a pivot there. So this is going to mean that h is not equal to 8. And let's go ahead and let's highlight that. Let's now look at our last one. This is when we have infinitely many solutions. When we have infinitely many solutions, we're going to have a row of zeros on the left-hand side and 0 on the right-hand side. So on our left-hand side, we're going to have h minus 8 equals 0. And then on our right-hand side, we're going to have to force k minus 12 to also be equal to 0. So this gives us a solution h is equal to 8 and k is equal to 12. So that's our solution when we have infinitely many solutions. In this question, we're going to use Gauss-Jordan elimination to find the general solution of the following linear system of equations. The first step that we're going to do is we're going to take our linear system of equations and we're going to put it into an augmented matrix. So our augmented matrix looks like this. And our right-hand side is 8, 1, 10. To do Gauss-Jordan elimination, we're going to work down and to the right. So the first thing that we're going to do is circle our first pivot. And then I'm going to highlight the entries below that pivot because those are the entries that we have to set equal to 0. So the row operations that we're going to use to get rid of the -1 is we're going to take row 2 and we're going to replace it with row 2 plus row 1. And then to get rid of the 3, we're going to take row 3 and we're going to replace it with row 3 minus 3 times row 1. Let's go ahead and do that. Our first row is not going to change, so we'll go ahead and we'll write that down. Now our second row, we're going to take row 1 and add it to that second row, so we get a 0, a -1, a 5, and a 9. And then in the third row, we're going to get rid of the 3, and we're going to take -3 times row 1 and add it to row 3. And that's going to give us a 0, a -10, a -2, and then a -14. We're now going to work down and to the right, and we're going to circle our next pivot, and then we're going to get a 0 below that pivot. To do that, we're going to take row 3 and we're going to replace it with row 3 minus 10 times row 2. This is going to give us the following matrix. Our first 2 rows are going to stay the same, so we'll go ahead and write those down. And then our second row is going to change. We're going to take row 2, multiply it by -10, and add it to row 3. And this gives us a 0, and then we get a -50, -2. So we have a minus 52, and then we have a minus 90, minus 14, gives us a minus 104. Now we're going to continue to work down and to the right. So we're going to circle our pivot. At this stage, we're going to start the backward algorithm where we need to make sure that every pivot is equal to 1. So what we're going to do is we're going to take row 3 and we're going to replace it with row 3 divided by minus 52. Here's what we get. Our first 2 rows are going to be the same. And then our second row, we're going to divide by minus 52. So we get a 0, 0, 1. And then it's nice that 52 goes into 104 2 times. So we get a 2 on our right-hand side. Now what we're going to do is we're going to work up and to the left. That's called the backward phase of our algorithm. And what I'm going to do, I'm going to highlight now in blue the entries that we have to make equal to 0. So let's go ahead and let's write down these row operations. We're going to take row 2 and we're going to replace it with row 2 minus 5 times row 3. And then we're going to take row 1 and we're going to replace it with row 1 minus 2 times row 3. Let's go ahead and let's do that. When you do the backward phase of the algorithm, I know it seems awkward, but you want to write down the last row first, because what we're doing is we're holding the last row fixed and we're changing the rows above it. So our second row, we're going to get by multiplying row 3 by minus 5 and adding it to row 2. So we have a 0, a minus 1, a 0, and then we pick up a minus 1. Now we're going to change row 1. We're going to multiply row 3 by minus 2 and add it to row 1. And this gives us a 1, 1. We get a 0. And then on the right-hand side, we're going to get a minus 4 plus 8 gives us a 4. We're almost done. Now what we're going to do is we're going to work up and to the left. So the next pivot that we're going to circle is this one. We need that pivot to be equal to positive 1. So what we're going to do is we're going to take row 2 and we're going to replace it with row 2 divided by minus 1. Our bottom row is the same, 0, 0, 1, and then we have a 2 on the right. Our second row, we're going to multiply by negative 1. So we get a 0, 1, 0, and a 1 on the right-hand side. And then our first row stays the same. Now we're going to circle our pivot again. It's equal to 1, so that's great. Let's go ahead and let's highlight the entry above it that we need to make equal to 0. So to make this entry to 0, what we're going to do is we're going to replace row 1 with row 1 minus row 2. Give ourselves a little bit more space here. So our last row and our middle row are going to stay the same. You'll get used to writing these rows in this order. And now our top row is going to change. We're going to multiply row 2 by minus 1 and add it to row 1. And we get a 1, 0, 0. And then a 4 minus 1 is equal to 3. Now we have our answer in reduced echelon form. We're going to go ahead and we're going to circle our pivots. And then we're going to solve for those pivot variables. Let's look back up here at the top. Our variables were x1, x2, and x3. So we can read off going across the first row, we have x1 is equal to 3. Across the second row, we get x2 is 1. And then across the third row, we get x3 is equal to 2. The really nice built-in check that we can do is we can take these answers and we can go back up to the top plug them in and make sure it's right. So let's go ahead and put this in our head. We have 3, 1, 2. So what we're going to do is we're going to say, okay, so x1 is 3, plus x2 is 1, plus 2 times 2 is 4 is equal to 8. That works. And then we're going to have minus 3, minus 2, plus 6 is equal to 1. That checks out. And then lastly, we're going to have 9 minus 7 plus 8 is equal to 10. And our left-hand side is equal to our right-hand side. So that way we know that when we got all the way through that complicated algorithm, we came up with the right solutions. In this problem, we're going to find the general solution to this linear system of equations whose augmented matrix is given below. So let's emphasize that this is an augmented matrix. As soon as you see that, I would suggest that you take a line and you put it right there. And that way you know you don't have a coefficient matrix, you have an augmented matrix, and you can distinguish the left-hand side from the right-hand side. To solve this problem and find the general solution, what we're going to do is we're going to take our linear system and we're going to put it in reduced echelon form, and then we're going to just solve for our pivot variables. Let's go ahead and let's do that. I'm going to start by copying down our matrix. That's always a good idea. I always talk to my students about checking their work. One thing that I've noticed is many students will make a mistake when you start your problem and you write down your matrix. So I would suggest after you write down your matrix, glance back and make sure that you did not make any copy mistakes. That's what I'm doing right now. And I see, okay, I have the right matrix. Now we can go ahead and start. It looks like this matrix may be already in echelon form. Let's see. Let's circle our pivots. And we can see it is in echelon form. Now all we have to do is put it in reduced echelon form. So when we do it in reduced echelon form, we're going to start with our rightmost pivot and we're going to work up and then to the left. So the entry that we have to get equal to 0 is that one right there. To do that, the row operation that we're going to use is we're going to take row 1 and we're going to replace it with row 1 plus row 3. Let's go ahead and do that. Let's go ahead and let's do this. Since we're doing the backward phase of the algorithm, we're going to write down our last row first. That row doesn't change. Our second row also doesn't change, so we'll go ahead and write that down. And then it's our top row that's going to change. So we're going to take our bottom row, row 3, and add it to our top row. And we're going to get 1 minus 3, 0, 0. We're going to pick up an 8. And then 5 minus 2 gives us a 3. Now let's circle our next pivot. Again, we're going to work up and to the left. So that's the pivot that we're going to circle. And we're going to get a 0 above that pivot. The row operation that we're going to use is we're going to take row 1 and we're going to replace it with row 1 plus 3 times row 2. Give ourselves a little bit more space here. All we have to do now is we just have to change our top row. So let's go ahead and let's write down our bottom row first. And then we'll write down our second row. And then lastly, we're going to change our top row. We're going to multiply row 2 by 3 and add it to our top row. So we get a 1, 0, 0, 0. We have a minus 15 plus 8 gives us a minus 7. And then a 3 times 3 is 9 plus 3 gives us a 12. And our matrix is now in reduced echelon form. I'm going to circle the pivots. You always want to do that when you get done because those are the variables that you're going to be solving for. You're always going to solve for your pivot variables. The columns in your matrix that do not have a pivot, such as this column and that column, are going to be your free variables. So let's just make a note. I always like to make my notes in pink. So this column is our third column, so we're going to say x3 is free. And then this is our fifth column, so we're going to say x5 is free. Now what we're going to do is we're going to solve for our pivot variables. So our first pivot variable here is x1. So we have x1 minus 7x5 is equal to 12. And I said we're going to solve for x1, so here goes. So x1 is going to be 12 plus 7x5. Now we're going to go ahead and we're going to solve for x2. So we're going to write down x2 minus 5x5 is equal to 3. So that tells us that x2 is 3 plus 5x5. Let's go ahead and write down that x3 is free. That way everything will be in order. Now we can solve for x4. So that is going along our last row. So we have an x4 plus 8x5 is equal to 5. So that tells us that x4 is 5 minus 8x5. And then lastly, we're going to write down that x5 is free. Let me go ahead and circle this in red so you can see that that's our final solution. For this question, we're asked to give a geometric description. Let's go ahead and let's highlight that. Geometric description of the span of V1, V2, and V3, and then we're given vectors V1, V2, and V3. Let's go over a little bit of theory before we go ahead and dive into the solution of this problem. What you need to know to solve this problem is that the span of V1, V2, and V3 is just a linear combination of those three vectors, and we can write that as C1, V1 plus C2, V2 plus C3, V3. In order to find the geometric description of our span, we need to determine the linear independence or dependence of our v vectors. The way that we're going to do that is we're going to take a matrix and we're going to put vectors v1, v2, and v3 in it. And then we're going to take that matrix and we're going to put it in echelon form. And then we're going to count the pivots. Let me show you how to do this. We're going to take a matrix and we're going to put our three vectors in it. So we have 1, minus 2, minus 5, 2, 5, and 6, and then 7, 4, minus 3. We need to put it in echelon form. So I'm going to start by circling our pivots. That's our first pivot. And we need to get a 0 below those pivots. Let's go ahead and let's write down the row operations that we're going to use. So we're going to take row 2 and we're going to replace it with row 2 plus 2 times row 1. And then we're going to take row 3 and we're going to replace it with row 3 plus 5 times row 1. Let's go ahead and do this. Our first row is going to stay the same. Our second row is going to become a 0, and then we're multiplying the first row by 2 and adding it to our second row. So we have a 4 plus 5 gives us a 9, and then we have a 14 plus 4 gives us an 18. Now we're going to change our third row. We're going to multiply row 1 by 5 and add it to our third row. So we get a 0, and then we have a 10 plus 6 is a 16, and then we have a 35 minus a 3 gives us a 32. Now I want you to look at rows 2 and row 3. Notice in those rows, the numbers in those rows are multiples of each other. So what I'm going to do, and I always tell my students, I call this like housekeeping. We're going to take row 2 and we're going to replace it with row 2 divided by 9. And then we're going to take row 3 and we're going to replace it with row 3 divided by 16. That's called scaling, and it's just going to make our matrix a little bit easier to work with. So we have a 1, a 2, and a 7, and then we have a 0, 1, 2, and then look at that. We have another 0, 1, 2. Whenever you have a row that's a repeat of a row, what's going to happen is that row is going to go to 0, because what we would do is we would take row 3 and we would replace it with row 3 minus row 2. So I always tell my students, whenever you see a repeated row, you can automatically know that that repeated row is going to go to 0. Let's go ahead and write that down. Our first two rows are the same. So we have 1, 2, 7, 0, 1, 2, and then 0, 0, 0. Now, what we're after is the geometric description. So that means we have to know how many vectors, v1, v2, and v3, we have to know how many of these are linearly independent. So if we circle our pivots, we can see that we have 2 pivots. So that means that we're going to have 2 linearly independent vectors. So our geometric description is going to be based on that. Let me just kind of summarize here. If you have 1 pivot, the geometric description is going to be a point. If you have 2 pivots, it's going to be a plane. And then if you have 3 pivots, it's going to be what we call 3D space. So our geometric description is going to be a plane in, now we have to go back up. Notice that our vector has 3 entries. So that means our vectors are elements of R3. So if we go back down here, that means our geometric description is that the span of these 3 vectors is going to be a plane in R3. A geometric description will include what we call an object and then the Euclidean space where the vectors are located. In this question, we're asked to find the value of h. So there's an h, and let's look down here. There's our h and our b. So for what value of h is b in the span of a1 and a2? So in other words, all we're having to do is we're going to pick a number for h so that our vector b is in the span of a1 and a2. Let's talk a little bit of theory before we go ahead and solve this. The span of a1 and a2 is just all the linear combinations of a1 and a2, and we can write that as c1a1 plus c2 times a2. Our vector b then is in the span of a1 and a2 if b can be written as a linear combination of a1 and a2. In other words, if b is equal to c1a1 plus c2a2. What we're going to have to do to solve this problem is we're going to take a1, a2 and augment it with b. That comes from this equation right here. And we're going to put that equation in echelon form, and we're going to see if a solution exists. Let's take a matrix, and we're going to put A1 in our first column, and then A2 in our second column, and then we're going to augment that on the right with our vector B, 4 minus 4H. Now what we have to do is put this matrix in echelon form. So let's circle our pivot, and then I'm going to highlight in yellow the entries that have to go to 0. And let's write down the row operations that we're going to have to use. We're going to take row 2, and we're going to replace it with row 2 minus 2 times row 1. And then we're going to take row 3, and we're going to replace it with row 3 plus row 1. Let's do this. Our first row is going to stay the same, so we can just copy that down. Now let's change our second row. We're going to take minus 2 times our first row and add it to our second row. So we get a 0. We get a 14 minus 10, which gives us a 4. And then we get a minus 8 minus 4 gives us a minus 12. Our bottom row, we're just going to take row 1 and add it to row 3. So we get a 0. We pick up a minus 4. And then we get an H plus 4. Let's go ahead and let's circle our next pivot. And then the negative 4 below that pivot is going to have to go to 0. So the row operation that we're going to use to do this is we're going to take row 3 and we're going to place it with row 3 plus row 2. I think I'm going to go down here so we have a little bit more space. Here's what we're going to get. Our first 2 rows are going to stay the same. And we add our second row to our third row, so we pick up a 0, and then we have an H plus 4 minus 12. Let's go back up here to some of our theory. What we wanted to do is, in order for B to be in the span of A1 and A2, we had to see if this matrix that we just constructed has a solution. So let's come down here and let's look at our last row. Notice for a solution to exist, we're going to have to force this, which is H minus 8, to be equal to 0. Because we can't have 0 equal to a non-zero number. So this is going to give us a solution that H is going to have to equal 8. So when H is equal to 8, let's go back up here. Let's go ahead and mark this as 8. When H is equal to 8, B is in the span of A1 and A2. In this question, we're asked to write the following linear system of equations as a matrix equation. Let's go ahead and highlight that. And then as a vector equation. A matrix equation looks like this. We have a matrix A times a vector X is equal to a right-hand side, which we typically call B. So what we're going to do is we're going to take our linear system right here, and we're going to divide it up into a matrix times a vector X times a right-hand side. Our matrix A is going to be 1, 2, 2, 3, and then 4 minus 6. And notice that we have an x1 and x2, so that goes into our vector X. And then we have a right-hand side, which is equal to 4, 5, and 8. So that's how to write a linear system of equations as a matrix equation. Now let's go ahead and let's write our linear system as a vector equation. I think this one is always a little bit harder because you have to remember what the form of a vector equation looks like. So a vector equation looks like this. We have x1 times a1 plus x2 times a2 is equal to our right-hand side, b. The x1 is all by itself, so let's pull the x1 out. Then we're going to create a1. So a1, if we look back at our linear system up above, it's going to be those constants. And then our a2 is going to be those constants. So our A1 is 1, 2, 4. and then we add x2, and we have our a2, which is 1, 3, minus 6. And then on the right-hand side, we have our vector b, which is equal to 4, 5, and 8. And that's how to write a linear system of equations as a vector equation. In this problem, we're going to show that the equation ax is equal to b does not, let's highlight that, not have a solution for all b. And we're going to describe the set of b for which ax is equal to b does have a solution. I wrote down in purple here what we have to do to solve this problem. We're going to take our matrix A, augment it with our right-hand side B, put it in echelon form. Echelon form is always the form that you go to when you want to find out if a solution exists. And then once we have it in echelon form, we're going to find restrictions on our right-hand side, which contains the variables b1 and b2. So let's go ahead and let's start. We're going to write down our augmented matrix. And then on the right-hand side, we have b1 and b2. We're going to put it in echelon form. So let's circle our pivot. And we're going to get a 0 below that pivot. So the row operation that we're going to use is we're going to take row 2 and we're going to replace it with row 2 plus 2 times row 1. Let's go ahead and let's do this. Our first row stays the same, so we'll go ahead and write that down. And then our second row, we're multiplying first row by 2, adding it to the second row, so we pick up a 0. And then we have a 2 minus 2, so we pick up another 0. And then we have our b2 plus 2 times b1. Let's now focus on our second row. The idea was we wanted to make sure to find the set of b for which ax is equal to b does have a solution. So when we look at this pink highlight, we can see that we're only going to have a solution when this is equal to 0. So that's when 2b1 plus b2 is equal to 0. We can go ahead and let's solve for b2. So this is when b2 is equal to minus 2 times b1. So our vector b, which was b1, b2, we can now write as a b1 and a minus 2b1. And then we can pull out the b1 and write this as 1 minus 2. So there's often two ways to write this solution. One way would be to just say that it's going to have a solution if 2b1 plus b2 is equal to 0, or you might be required to show that vector b has to be in the form b1, 1 minus 2. In this question, we're asked to determine whether each of the following statements is true or false. Let's go ahead, and what we're going to do is we're going to work through these one part at a time. So let's first look at part A. In part A, it says for each b in Rm, the equation ax is equal to b has a solution if and only if the matrix A has a pivot in every row. And we need to decide if that's true or false. I've actually written down the solution for this, and let me kind of walk you through it. We're going to start by looking at the size of A, X, and B. And the reason that we're going to do that is that they say for each B in Rm, so we kind of have to make sense of that. A is m by n, And to make the multiplication work, x has to be an n by 1 vector. And then by default, what you're going to do is you're going to cross these out. And then b has to be an m by 1 vector. And that's why they say that b is an element of our m. Okay, so that part's okay. Let's go back up and read it again. It says if each b and rm, so we got that down, the equation ax is equal to b has a solution if a has a pivot position in every row. Okay, so that's what we have to focus on, that a has a pivot in every row. So what I've done here is I've just written down a matrix where A has 3 rows, where A is a 2 by 3 matrix, and then we have a right-hand side. So I'm just trying to envision what it looks like if we have a pivot in every row. If that happens, we have a pivot here, and we have a pivot here. This means that every row has a pivot, so we're going to have no restriction on B1, B2, and B3. So there will not be a restriction on B1, B2, B3, all the way up through BM. And because there's no restriction, we say that AX is equal to B will have a solution for all B. So this statement is true. Let's now look at our second statement. Our second statement says that if A has a pivot position in every column, the columns of A span Rm. Just like we did for part A, I'm going to start out by saying, okay, A is M by N, and what the problem told us is that it has a pivot in every column. So I said, okay, so every column is going to contain M entries. And often you guys, when you're doing problems like this, it really helps to write down a matrix. So I just said, okay, what if we have a 3 by 4 matrix? And then I wrote X's for our entries just to get an idea of the structure. And our problem, part B, says that A has a pivot position in every column. So what I did is I circled these to indicate that we have a pivot in every column. And then the question says the columns will span R3. Notice in this example that I have a column without a pivot. So this statement is actually going to be false because the columns will span R3 if every row, not column, has a pivot. So we're going to mark this statement as false. Now let's look at our last one. So this is part C, and it says the columns of A span Rm if and only if each B in Rm is a linear combination of the columns of A. Okay, so we have to focus on B being a linear combination of the columns of A. So what I did is I reasoned through this. I said, okay, if each B in Rm is a linear combination of the columns of A, that's what our statement said, then what's going to happen is we're going to have no row of zeros, and that means that every row is going to have a pivot. And when every row has a pivot, the columns span Rm, so that tells us that this statement is true. In this problem, we're asked to use an augmented matrix to solve the matrix equation AX is equal to 0 and AX is equal to B. We're then asked to write the solutions in parametric vector form and then provide a geometric interpretation and comparison of the solutions. Okay, we got a lot to do. what I wrote down in purple is how we can go ahead and get started on solving this. What we're going to do is we're going to take matrix A and we're going to augment it on the right by 0 and B. The reason that we're going to do that is we're going to want to solve both of these equations at the same time so we don't have to do repeated row reduction. We're then going to take this augmented matrix and we're going to put it in reduced echelon form, and we're going to solve for our vector x, and we're going to write our solution as a vector. That's what it means when we have to write a solution in parametric vector form. To start, we're going to take our matrix A and we're going to augment on the right with 0 and then our and then our vector B. So we have a 1, 4, minus 1. I'm just writing down our matrix A. And on the right-hand side, we have our 0 and then our B. This method is really nice if you have a lot of vector B's like B1, B2. You can do them all at once. Okay, so we need to put this in reduced echelon form. So I'm going to start by circling our pivot, and then I'll highlight these two because those are the entries that are going to have to go to 0. I'm going to write down the reduction that we're going to do. We're going to take row 2, and we're going to replace it with row 2 minus 2 times row 1. And then we're going to take row 3, and we're going to replace it with row 3 plus row 1. Our first row is going to stay the same. So we have a 1, 4, minus 1. And on the right-hand side, we have a 0 and an 8. And then we're going to multiply our top row by minus 2, add it to our second row. So we get a 0, a 0, a 0, a 0. Ah, it's all 0. And you know what? I think our last row is going to look like that too. We're going to take row 1 and we're going to add it to row 3. And we're going to get all zeros. Now let's go ahead and let's circle our pivot because that's the variable that we're going to solve for. Now we're going to have two solutions. Let's first find the solution to a times x is equal to 0. So that means we're going to use our 0 for our right-hand side. So we have an x1 plus 4x2 minus x3 is equal to 0. We're solving for x1 because that's our pivot variable. So we have x1 is equal to minus 4x2 plus x3. Let's now write our solution x in vector form. So I always tell students, write down your x first and then plug in. See, your x is going to be x1, x2, x3. Now we're going to go ahead and we're going to plug in. We're going to plug in for x1, so minus 4x2 plus x3. And then x2 and x3 are free. So that means they're going to go in as themselves. This is often a mistake students make. Those guys just go in as themselves. Now we can go ahead and we can split this up into a vector that multiplies x2 and a vector that multiplies x3. So we'll pull out an x2 and we have the vector minus 4, 1, 0. And then we have our vector x3 and the vector 1, 0, 1. That is our solution to a times x is equal to 0. Now we were also asked to give a geometric interpretation of the solution. So notice that we have two vectors and two free variables. If we have two vectors, we'll always have two free variables. So the number of vectors is going to determine the object. When we have two vectors, we're going to have a plane. So we're going to have a plane, and then we got to tell where the plane's located. We have 3 entries to our vector. So that means our vector is going to be in R3. So our geometric description or interpretation is that it's going to be a plane in R3. Now let's go ahead and let's solve A times X is equal to B. Let's go back up here and take a peek. We're going to have the same thing. We're going to have x1 plus 4x2 minus x3. And now instead of a 0, we're going to have an 8 on the right-hand side. We'll solve for x1. So our x1 is minus 4x2 plus x3 plus 8. Our vector x is again x1, x2, x3. We're going to plug in for x1. So we have a minus 4x2 plus x3 plus 8. And then x2 and x3 go in as themselves, just like they did. Now we're going to go ahead and split this up. We're going to pull out an x2, and we have the vector minus 4, 1, 0, just like we did above. And then we'll pull out an x3, and we have a 1, 0, 1, just like above. Now here's what's going to be different. We're going to have an 8, and then think of x2 as adding 0 and x3 as adding 0. So our vector on the right is going to be an 8, 0, 0. Again, we have two free variables. So that means we have the linear combination of those two vectors plus a vector 8, 0, 0. So the geometric interpretation of this, it's going to be a plane in R3. But now here's where the difference comes. This plane is going to pass through our point 8, 0, 0. To contrast this to our solution to AX is equal to 0, for that solution, we said that it is a plane in R3. Now let's go ahead and add that it's through the origin. You can visualize it as adding the point 0, 0, 0. Now we can compare these two. These two planes are going to be parallel. So we can say that our solution to AX is equal to B is a plane in R3 through 8, 0, 0. And we can add that it is parallel to the solution A times X is equal to 0. In this problem, we're going to find the value of H for which the following vectors are linearly dependent. Let's notice that H is down here in vector V3. Let's talk about a little bit of theory before we dive into the solution of this problem. Vectors will be linearly dependent if the linear combination of these vectors C1v1 plus C2v2 plus C3v3 is equal to 0 has a non-trivial solution. That means a solution that is not equal to 0. So in practice, here's what we have to do. We have to start with a matrix, and in that matrix, we're going to put vectors v1, v2, and v3. We're then going to put it in echelon form. The reason for this is that we want to see what type of solution we have. And we're going to choose H so that there is a column without a pivot. Whenever we have a column without a pivot, we are going to have a non-trivial solution. If every column has a pivot, the only solution to this equation right here is going to be that C1, C2, and C3 are equal to 0. So what we're going to do is we're going to have to force it to have a column without a pivot. So we're going to take our matrix and we're going to put vector v1 in the first column. So we have a 3, -3, and a 6. We're going to put vector v2 in the second column, and then vector v3 in our third column. And we're going to put this in echelon form. So I'm going to start by circling our pivot, and then I'm going to highlight the 2 entries that have to go to 0. The row operation that we're going to use is we're going to say that row 2 is going to go to row 2 plus row 1, and then row 3 is going to go to row 3 minus 2 times row 1. Let's go ahead and let's do this. Our first row stays the same. And then our second row, we're going to add our first row to it. So we're going to get a 0. A -9 plus 6 gives us a -3. And then a 2 minus 2 gives us a 0. Now we're going to change the third row. We're going to multiply the first row by -2 and add it to the third row. So we get a 0. We pick up a -12 plus 11 gives us a -1. And then a 4 plus h. So we'll write that as h plus 4. Now let's circle our next pivot. It's going to be a lot easier to work if this pivot is equal to 1. So what we're going to do is a scaling, and we're going to take row 2, and we're going to replace it with row 2 divided by -3. So our first row is going to stay the same. Our second row, we're going to divide by -3, so we get a 0, 1, 0. And then our third row stays the same. Now let's go ahead and let's circle our pivot. And this -1 is going to have to go to 0. So we're going to take row 3 and we're going to replace it with row 3 plus row 2. We'll give ourselves a little bit more space. Our first 2 rows are going to be the same. So we have a 3, 6 minus 2, and then a 0, 1, 0. And now we're going to take our second row, add it to our third row, and we have a 0, 0, h plus 4. Now, in order for our vectors to be linearly dependent, we have to have a column without a pivot. Let's go ahead and let's circle our pivots. And we can see that the only way that we can have a column without a pivot is if we make this pivot equal to 0, which means it's not going to have a pivot. So here we go. We're going to take h plus 4, and we're going to set it equal to 0, and that's going to give us an answer that h is equal to -4. So when h is equal to -4, we have a column without a pivot, and our vectors are going to be linearly dependent. If we wanted our vectors to be linearly independent, we would have to make sure that h plus 4 was not equal to 0. In this question, we're going to determine by inspection, that means we don't have to do any row reduction, whether the vectors are linearly independent or linearly dependent. I often tell my students these are like our special cases. Let's start by looking at problem A. In problem A, what I want you to notice is that we have a vector v2 and it's equal to 0. So let's write that down. So I'm going to write down that v2 is a 0 vector. And whenever we have a set of vectors and one of the vectors is the 0 vector, that set is linearly dependent. So we'll write down linearly dependent. Let's now look at part B. In part B, what we need to notice is that there might be a relation between V1 and V2. So let's go ahead and let's start. Let's look at these numbers. Do you see that if we multiply -2 by -4, we're going to get 8? Let's see if that holds. If we have a 4, multiply it by -4, oh, it does. We get a -16. And then 1 times a -4 is a -4. So we can write down that V1 is -4 times V2. So this means that these vectors are multiples of each other. And whenever you have two vectors that are multiples of each other, the vectors are linearly dependent. Even if you have 3 vectors and 2 of them are multiples of each other, the set will still be linearly dependent. Let's now look at part C. At part C, I want you to notice that we have 3 vectors and each vector has only 2 entries. So I'm going to write this down as more vectors than entries in each vector. Whenever you have a case like this, the vectors are linearly dependent. The reason for this is if you were to put V1, V2, and V3 in a matrix and row reduce it, because of the structure, every column could not have a pivot. So you're always going to have linearly dependent vectors. Let's now look at part D. At part D, we have 2 vectors, and let's see if they are multiples of each other. So if we start with 1 and we multiply it by 2, we get 2. If we take 4, multiply it by 2, we get 8. And then if we take 5 and we multiply it by 2, we would actually get 10, and instead we have a 3. So that tells us that V1 and V2 are not multiples. We can write this algebraically as V1 is not equal to K times V2. So we have 2 vectors and they are not multiples of each other. So that means our vectors are linearly independent. Be sure to check out the next review video on linear transformations.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.